let's start about this memory organization. So this is after data pipelining. This memory part is having strong effect on your software performance. So we will see with some examples how they are actually affecting. So memory, these are okay. I think these are very basic. That there are two types of memories: volatile and non-volatile. Where for volatile memories whose contents are lost when the power is cut off, and the example is RAM. For within RAM again we have static RAM, dynamic RAM, and they have their own advantages. That static RAM is, what is it? That is faster, but it takes up more silicon area, and it is very costly also. So in spite of the fact we prefer static RAM in terms of performance, we cannot always use that. So another, our option is dynamic RAM, which is not so costly, but of course, which is not as fast as well. We have some non-volatile options. Those are read-only memory, where we can retain our data even if the power is not there, power is turned off. And for the examples of non-volatile memories are that you have EEPROM, flash memories. Flash memory is also some sort of EEPROM, but with some added changes. So I will share some links. So I will discuss about very basic architecture and what are the things that will be directly affecting our software design performance. But I will share a few added links where you can go and check how different types of flash memory choices also can affect your design. Design performance. So a few terms I think that is known to you. Register, that is most integrated memory tightly coupled with our CPU. And this cache part we'll discuss later on. That is the intermediate, smaller, faster memory residing between our processing unit and our main memory. But whatever happens, when you are writing as a software designer, when you are writing a program and it is execution, from the software designer's point of view or from the programming point of view, we consider that our memory is contiguous. What does it mean? Whenever we are writing and executing the program, we are considering that we have some address space where our instructions are getting mapped. Remember the blocks in the pipeline, whatever we have discussed, our instruction memory is fetching, storing in some contiguous way, and we are fetching the instructions from there. From data memory, we are fetching, we are executing our pipelining steps, etc. Things are not so straightforward. Actually, whenever we are considering, whenever we are writing the program in our, and there is some CPU execution, the concept of memory we are using, that is logical address space. Okay. But actually that logical address space is not with the same, may or may not be with the same size of your physical address space. What does it mean? That is this logical address space that is generated by your CPU. Okay, that's why we are considering that as virtual address space. But this address space, it is directly related to your software. But that is not exactly what is getting mapped to your backend actual hardware memory unit. Why is it required? Whenever you are in execution, or whenever you are actually writing a program or considering a program, the required address space may or may not be whatever physical memory, exact direct main memory support you have. That may be bigger than that. So for that, you use external address space, and somehow you have to fetch whatever in that extra address space to your memory, because your CPU or processing unit can only understand this main memory. Okay, so we may think about this this type of representations where we have some main memory, this is your user space, and you have some backing store of memory. Okay, so of course, whenever you are executing some process P1, process P2, whatever may be the case, you are fetching some process related memory related information to your main memory, and if some process has completed its execution or not in execution at that time for your processor, you may be swapping out to their backing store. So that way, in spite of the fact whatever processes you are considering, if the total memory is larger, very larger than your main memory, then also you are managing the execution of your different processes. So this is a very important concept when we are thinking that in spite of the fact we are seeing that different processes are in execution, maybe in the same processor, but actually the memory related mapping is directly going through some swapping techniques, some in and some out. Okay. So if we think about now this contiguous memory allocation, let's say some process is there. Maybe this is the process A. This process A, the related memory is getting mapped. And whenever there are different processes, their memory is getting mapped to the main memory. And for that, whenever CPU is creating some logical address, it is sending some address request to the memory portion, there is a check for that whether actually memory can allocate that much of address or not, at that much of memory or not. So there are some limit registered to check whether your required address request is within the threshold or not. If yes, then through this relocation register, you're adding this your logical address request, and that is getting mapped to your main memory. So this is the basic idea when we think about any kind of contiguous allocation. That means for a particular process, whatever memory request we are sending to the memory, that logical address request is getting appended with some relocation register. And that relocation register may be giving you the idea from where in your main memory this address allocation will start, and then you will actually that virtual memory, that logical memory will get a mapping in your main memory. Okay. In case of logical address, when you are writing your program, you know that any C program, whatever, I'm not going to the C program, I mean any language you are following, you are dividing your main program in different components, different segments. So user space, user view of a program, if we think, it is divided into some components. So it may happen that these components, they are getting mapped to the user memory, but not in that same contiguous manner. You can see here there are different components and they are mapped in different parts of this main memory. Okay. So there are different concepts that which part you will map a certain address request, what are the base algorithm to choose that blocks, etc. We are not going too much details of that. So one topic is important when we are talking about this mapping of this virtual memory to some physical address space, and that is called paging. We can see with this diagram, I think that will be easier. paging concept tells you that you have divided, maybe here you can see, you have divided your logical address space into some fixed size blocks. Okay, and that those blocks are called pages. So logical memory you're dividing into fixed size blocks, that is pages, and physical memory you are dividing into some fixed size blocks, those are called frames. Okay, this way you are creating a mapping, and that is called the page table. That means nothing else. The page table is a mapping where you are keeping a track for which page, I mean when your CPU logical address is generating a page request. That means CPU is trying to execute a code for which you need some data or instruction fetch from a particular memory, and that block is with the ID, maybe page number P1. So you will check in this page table for that particular page what is your frame number. Okay, so this frame page table will provide this frame number, and then from this page table, page number with that associated feature in logical address here, offset. So what is the total maybe address and up to which part you will go. Okay. So this is the page number. From the page table you are getting a mapping of frame, and from that then the frame you will count the offset required, and that way you will get the physical memory from where you can actually fetch your required data for your processing. Okay, so this is the concept of paging, which basically maps your logical address blocks, smaller blocks, that is called, we are calling them as pages, to the frames present in physical memory. Okay, is it clear? Sorry. Any question? No, right? Okay. So if this is very straightforward paging to framing, I mean logical address to physical address mapping. But if we directly blindly implement this, of course you can think there will be huge number of pages, and there you have to maintain a table for each page. There will be some frame, and whenever your CPU is actually generating a particular page number, for that you have to maintain a huge search technique. That means there will be huge table from where you have to search your page to frame mapping, and then you have to supply that to your physical memory part. But that is very costly. So what is the intermediate solution? That we are actually considering one intermediate buffer. Buffer means, of course, you can store something. What you are storing here? You are storing the maybe some most recent page to frame mappings. Okay. So for this page map to frame mappings, what happens? If this TLB is holding that intermediate values, so whenever there is a request generated for this logical address to physical address mapping, the first search is taken in this TLB, translation Lucas array buffer. And then if there is a hit, that is called TLB hit, that means you have successfully found your page to frame mapping in this TLB, and that TLB hit result is sent with the given offset to fetch the physical memory, to map, I mean point to the physical memory. But of course there is a chance that whatever page you are actually searching, that is that is not present in the TLB cache or TLB buffer. That means you have not recently searched, or that entry is not already made in your this buffer. For that instance is called TLB miss, where you have to go again back to the page table. If there is a TLB miss, then you have to find this page to frame mapping. Okay. And then the usual thing that once you are getting that frame, then you will be adding that offset, and then you will search in the physical. And then you will get the location in the physical memory. So this is the typical idea of paging, which helps us to understand then whenever we are writing something, the memory we are thinking, it may or may not be the actual memory, the actual way we are thinking. There may be some backend support, backend storing support, from where we are fetching some memory, we are thinking some virtual memory concept, and we are there is the added technique that is paging. Paging basically a typical mapping technique where we are mapping from this, getting a map for this virtual memory, whatever we are thinking, to our actual physical memory, physical address in our physical memory. So for that, we understand the effective access time is, there will be two things associated. One is, whenever, yes?
Ma'am, could you please one more time explain that paging with the TLB thing? Like, I was not able to follow it.
Okay, for this TLB part. Okay, TLB is just a buffer. Yes. Okay, buffer means whenever your CPU is generating a logical address, ideally in our paging technique, what we do, we directly go to the page table, we try to find to this page to frame mapping, right? That is clear, right?
Yes, ma'am.
But here what we are doing, we are keeping an intermediate buffer, that is this TLB buffer. So, which is again storing maybe some most recently used this page to frame, mapping information. Okay, see, wait, this page to frame mapping information. So first, whenever this page number is getting generated, so the first search will be taken place in this TLB buffer. If it is found, that is good, that is considered a TLB hit. TLB hit means whatever page number you have given to that buffer, you got the frame number. Your ultimate objective is to get the frame number, because ultimately you are accessing the data from the physical memory, and that you can only do if you have the information about this frame number. Frame number means that which block of your physical memory you will access, and this is the exactly which part of that block you will access, that will be given by this offset. Okay. So if this buffer is giving the information of that frame, well and good, there is no point going further to the actual page table. If it is not giving you any information about your frame number, that means with respect to that page table, the frame number entry is still not there in your buffer. So for this reason, or that may be one thing. Otherwise, see, buffer is with some very small limited size, because if you keep this small buffer with the same size of your actual page table, what will happen? You will not get any advantage, because why you are using a buffer? So that in your page table you have some maybe n entries. From that n entries, maybe some most recent m entries you are keeping in this TLB buffer. That means whenever you are searching in this TLB buffer, your total search requirement is m. Whenever you are searching in your page table, maybe your total search requirement is n. And of course, you have to keep m much lesser than n, so that you can get some advantage of this TLB buffer. So that's why if there's a TLB hit, that is good, that you are not going to search this whole n rows again in the page table. If there is a miss, then of course you have to come back to this page table, you have to again search through those whole n rows, and then you have to fetch this frame. Okay, that is the advantage of using TLB buffer, that you are using much lesser amount. I mean, you can get your frame. If there is a hit, there is a possibility, there is a chance that you can get your frame number with much lesser search. Okay, clear?
Got. Yes, ma'am. Yes, ma'am.
Okay. But of course, whenever, now see the flip side of it. Whenever there is a hit, very good that we have done everything with some lesser search. But whenever there is a miss, what you have to do first, there is some m row search in your TLB, and that is of no use because you are not getting any information about your frame number. Again, you are going back to this page number. Again, you are searching in the full page table. That means you are searching in full m rows. So, instead of that, if you have in the scenario where you were not using this TLB buffer, directly you were that time searching only in these in rows. Whereas in case of TLB means what you are doing, you are first searching in that TLB m rows, and then again you are searching in rows. Of course, you can understand in case of TLB miss, there is a in number of increase of required amount of time, effective time. So that way, whenever we are considering this effective access time, what we have to consider? We have to consider some amount of heat ratio. This is the heat ratio. That means percentage of time that a page number is found in your TLB buffer. Okay, and 1 minus this alpha. Of course, if this is the heat ratio, you can understand this is a miss ratio. So whenever you are considering your effective access time, in worst case, you have to consider both the hit situation and the miss situation, considering your possible hit ratio and miss ratio that you have counted. So that way, effective access time should have the effect of both hit and miss. Now, why these points are important? These points are important only because of the fact whenever you are writing your software, you can write it blindly. You have your instruction set, and you have your specification. But we will see few examples where this knowledge of cache is important to analyze your worst case, performance time requirement. So not now. After you will study scheduling and those few RTOS related few another topics that Professor Sharper will take. And after that, at the end, whenever you will do this performance analysis, your worst case access time or WCET analysis for those cases, worst case execution time, these type of what is the effect of cache on your software design, those parts will come into picture, and for those analysis part, this information is very important. Okay, so this is very brief introduction about how you are actually mapping your virtual memory concept to your physical memory hardware. We will talk something about the cache memory also, but before that, just I want to show you something. Yeah. So this is from very basic book by Galvin's book, Operating System. So I will share this slides with you. Those who are not related to computer science background, maybe they are just studying, or those who are just studying this memory concept for first time. So you can go through the slides once. These are very basic but very detailed slides, I will say. That will clear you understanding about this virtual memory to paging concept, and that will also show you that this is not all about paging, because there are different types of paging techniques. You can come here, actually. this is whatever we have talked about, that is a very basic paging concept that you should know. But after that, you can come here. There are different types of paging. Okay. What will happen when you have shared pages? Because whatever you are telling, you are having one process, you are actually thinking of sending them in the backend store, and you are creating or considering some other page tagging whenever you are fetching another process to your main memory. Now, what about the shared pages? How will you handle them? And how to improve this paging technique with some hierarchy, where we can actually not only a single page table, you can actually use some hierarchical page tables. You can see they're using some outer page table. From there is a mapping to some inner page table, and from there is some mapping to memory. So that way, how two-level page table is actually helping you to improve the performance and do the address translation. So these are what is the advantage of hash table. There is another concept of inverted page table, where we think in the paging concept, we are starting our discussion from the concept of particular process. Whenever our CPU in execution, it is generating some logical address request. So related to that particular process, we are thinking about how that page is getting mapped to a frame, right? Here CPU is the inverted page table concept is a bit different, where you are just thinking that a single page table, where you are starting your thought process from with the reference of physical memory frames, not from the pages. So there are different advantages of that. So I'm not going to that much details, but if you are new to this and if you're interested, you can go to this. And based on that, you will see here are a few examples given. There are for these different types of processors, Intel 32, and then there is ARM processor, and there is x86. What are the different techniques? The concept is same for paging for all of these processors. But what are the different techniques they are actually, considering for their different purposes? So these few slides you can go. This is related to the ARM architecture, where you can see they are actually considering some outer paging technique and then inner paging technique, and then they are considering the offset. Basically, they are actually adding some hierarchy to the paging concept, and that is giving for some amount of improvement. Okay, so this is a few different types of memory architectures present in different processes that we have already talked about. Okay, so I will share this slide also, so you can go through this. That will help you to understand that what more there in the paging and what more different types of pagings followed in different types of architectures. Okay. So after that, we will be talking about cache memory. Okay. Okay. Any questions so far? Is it okay for everybody? Is ma'am audible? Am I audible to everybody? Hello?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Some chat is there. Okay. Okay. Next, we will talk about this cache memory. Cache memory means, you can see in this diagram first, that this is your ALU again. This is your ALU, main memory. Your main memory is huge and costly. No, not costly, I mean it is huge. So lots of friends are there. So of course it will take huge time to search for every instruction execution. If you directly send a request to the main memory, there will be that will be the such time will be more. So what technique we are considering? We are considering an intermediate, smaller, faster memory unit that is called cache memory. Okay. So there are different types of cache. We will come into that. So cache means what? This is maybe your main memory. You are actually copied a few intermediate blocks to your cache. Now you have to think in that way that what will be your technique or strategy and which blocks you will consider. Okay. So there are many types of cache. We will come into that after we complete our discussion about how this mapping takes place. But here we will start our discussion from our main memory. So maybe you can see this is our main memory where it is divided into different blocks. Okay. So whenever we are considering some huge memory and we are trying to map them to a smaller memory, what we need to understand that of course we cannot map all the blocks at a time, right? Here you can see this is divided into different blocks, and according to the color convention, you can see the red is, we are thinking that red is mapped to this red part of red. This you can see, say this is the cache line, and these blocks, this red blocks is mapped to this cache line, red cache line. These blue blocks mapped to this blue cache line, and so on. So this way you have to choose that some amount of blocks we will map to this cache number 1 based on the size of these smaller blocks present in your main memory. Also that will control what will be the size of these blocks in your cache memory. Number 2. Number 3, of course you can see these red blocks are also getting mapped to this part, and these blocks are also getting mapped to this cache line, right? So that means sometime, since this cache memory is smaller and your CPU is huge, so it is not possible that you will be mapping all the blocks to their cache memory at a time. So there must be some strategy how you will mapping these CPU blocks to your cache locations, and what will be your strategy to remove some blocks from the cache values. So in that way we will discuss those parts. So again, similar to our concept, whatever we have discussed in our TLB hit and TLB miss, the same concept comes here also in cache hit. That means in that intermediate small memory, since you could not copy all the blocks, whatever you have in your main memory, so there are some addresses, maybe this is the generated address from your CPU. That address you are checking with each of the cache line blocks, and this is the address of them that we can tell tag. You are checking that given address portion, sorry, not the whole portion, this address portion, and if this match, there is a match found, then you are checking which is the index. Index means you can come here, you can see that these are the based on the byte address, both are mapped to the same cache line. But these are the cache blocks, byte 0 and byte 1. Maybe that way to map this 2 cache blocks, each one of them, you need at least 1 bit, where the 0 will signify maybe you are pointing to the one cache block, 1 will signify that you are pointing to the other cache block. So that way, whenever you are sending the address and there is a match with this tag, next you have to check with which index you are fetching. Within that index, you have to fetch which part or which offset you are considering to fetch your actual data that is required for your CPU request. So if there is a match in the address and the tags, you can think these all other rows present, lines present in the cache, and they are associated with some tags. Tags means the address for which they are having a map. So that tag and that address, if you are comparing, and if there is a match, then, and also there is a concept of valid bit. Valid bit means some cache lines updated with some valid data. So both are true, then there is a hit, and after that, based on the index and the data value and the offset value, you are fetching the actual data that you are sending to the CPU. So before that, we can go here. Where is that? Yes. You can think in this way from this diagram. Maybe we'll come here later. That whenever there is a match of these tags, then you are checking which index, which block within those cache blocks present in the same line you will be fetching. Sorry, these are the blocks 0 to B-1. And when you are getting that exact block address, from there you are actually fetching what is the offset block offset value we will be considering. That part will be your data that will be sending to your CPU. Okay. So this is the concept of, okay, now we will see again, whenever we are thinking about this average memory access in this way, we have to consider what will be our average memory access time. So whenever we will also see in our execution time analysis that whenever our processor is mapped with some cache memory, we are having the support of the cache memory, of course we have to think the same way, that there is a chance of hit and also there is a chance of miss. So there must be some miss rate and miss penalty. The same way we have talked in virtual address to physical address mapping. The same concept here also. There is a possibility, since it's a cache, since it is also similar type of buffer. Of course, there is a possibility of miss that I have to take into account in my average memory access time, because whenever you are computing your overall total access time of your software, of your total execution time, that time this part is very critical. So there and now we will talk about few types of cache mapping. One is what we have seen, that is a direct mapping. Direct mapping means you have a tag and some address, that is, you have a tag from your address, total CPU generated logical address. You are searching in your cache memory, and if there is a match, that means for a particular location of cache, only that address is possible. Okay, what is it? Yes. Direct cache mapping means for a particular address or some few address blocks are possible in a particular location. That means you can go back to our first this diagram. See, we can see these red colored blocks are only can get mapped to these locations. These blue color to these blue locations. These blue to again to these blue locations, green to green and purple to purple. That means whenever in your due course of execution, maybe you are trying to fetch some instruction or code from this red zone. Okay, maybe you are here in this red zone and you are here in this next instruction also in this red zone coming from your red zone. In that case, since you are actually fetching your data or instruction from the cache, what you have to do? You have to replace one block. You have to send out one block from your cache, your first red block from your cache, you have to load the second red block set in your cache, and then only you can actually execute them. Get the access to that instruction or get the access to that logical physical address, right? So that way, few blocks, they are mapped to a particular single cache line. So that is called the direct mapping of your cache. Whereas, of course, you can understand that things are very restricted there. If few blocks can only be mapped to a particular single block, of course, there's a chance of repeated replacement. So totally opposite strategies. Okay, no need to have these type of restrictions. No need to have the restriction that a particular block from our main memory can be mapped to a particular set of blocks, so can be mapped to a single line. Consider the other way around, that any of these index blocks can be mapped to the whole cache memory in any location of the cache memory, like this. That means these tagged address 32 bits and whatever address you are generating, there is no concept of indexing, right? So any blocks can be placed anywhere, and in that case, your size of search is getting increased. See, previously when you are searching, you are only searching on this tag values. If your bit size of this tag address is maybe n bit, you were only making a n bit search. But here you can come here, you can see that there is no concept of index. So whenever you have to search in the whole possible or all the possible locations. So that way, for each such part, whenever you are searching any logical address, the mapping of for any logical address, any address search in your cache, at that time your search time is getting increased. And also this is very complex strategy. So that way, fully associative technique is not very widely used or not very acceptable solution when you are considering in practical scenario. So we will go in between. What we will think? We will consider the one concept of associativity. Associativity means what? We will consider the concept of sets. That means not that it is very fixed that one frame or one main memory frame can be one memory block can be mapped just to a particular cache block. It is also not the case that okay, one main memory block can be mapped to any of the possible locations. The in-between solution is that we will consider one set, and an empty block in the correct set may be used for storing data, and that whenever there is a mapping, that one block can be mapped to any of the blocks of this set within the set. That means rather than full associative, we are decreasing the associativity, and we are considering that based on our the way associativity. That means one way, two way, three way, means we have in one way we have, see, only it can be mapped to one block. That means this is quite similar. We should not discuss this because this is just like direct access, the whatever we have discussed previously. Here in two-way associativity, we have 4 sets, okay, and in 2 blocks each. So whenever I'm mapping any block, that any block can go to any of the two blocks in these sets. Okay, it is not fixed. Initially, it was fixed that one block will go to a particular one single location. Now your possibility is increasing that one block can go to any of these two locations, or in case of four blocks each, any block can be mapped to any of the blocks whichever it is free. So that means you can understand here there is a improvement in terms of possibility of cache miss. That means whenever you are having any block field, you are now not searching to a particular location or particular block. You are searching in a particular set. So whenever there is the one block of that set is filled, you are basically searching in the next block. You are checking if it is not, if it is empty, you are actually placing that there. So there is less requirement of replacement also. That way, if we can actually minimize that block replacement, if in the next instruction execution, we are again actually trying to feed some instructions from this block, we are already having that block in this cache memory. Okay, so for that case, again, if this is the four-way cache, again, whenever we are getting one block is filled, we are checking other three first, and if any of them is empty, we are just placing there. That means other three blocks, if there was some data already added in the cache, they are retaining at that location. What is the advantage? It may happen in coming instructions if we are actually trying to fetch some data on any of these four locations, no blocks are replaced. That means again there is no, if there was a replacement and again and let's say this block had been replaced by any of the main memory blocks, new blocks actually, then in our next instruction, maybe that was the case when you are in instruction is 0. S10 maybe, S10. When you are in instruction S11, again, if you are trying to get the previous data that was present in this block, there's some data from that was present in this block, but now that block has been replaced. That means again you are getting some cache miss. Again, you have to go back to the main memory and you have to fetch that data. And the whole process of searching in the cache, then getting a miss, then again going to the main memory, everything you have to do it again. You have to bring the data back in cache, and then only CPU can execute from there. So with this n-way, we can say k-way or n-way set associativity. Of course, we are trying to improve the performance by reducing the number of cache misses. Okay, so that is the concept of cache and block replacement in cache. Okay, so this is the example of a two-way set associative cache. You can see here, whenever you are getting some address, what you are getting, you are getting that tag, you are getting some index, and you are getting the block offset. Okay. Now here what happens, these tags again you are checking. Okay. Now you are not checking only with one single, blocks of one particular set. There is a possibility that any of the, if it is a two associative, of any of the two blocks of your set can hold that data. So that way you are searching. If there's a miss, there's a hit. Of course, also you're checking this valid entry, whether that is cache block is actually containing some valid data entry. You are fetching this, and that way your possibility that data is for your immediate instructions, the data is retaining in your cache, the chance is higher. Actually, we will see one example, I think, that will. Okay. See this example, okay? That is maybe clear the concept. Sorry. So see this. This is a following cache. So this example shows how you will do the indexing. Okay. When you can see, actually you can reduce this, it will be better. There is higher order bit. There are two concepts. One is higher order bit indexing and middle order bit indexing. That means you can see when you can see this pink blocks and the addresses associated with it. All 0, all 01, all 0010, 0011. Okay. So whenever you are doing this high order bit indexing, what happens? For this all 0, this bit, you can see the 4-line cache in the left. Okay. So here for all 0 in the high order, all are coming to your pink block in your 4-bit cache line. 4-line cache. Whereas in your middle order bit indexing, you can see you are doing based on that 0001, 0010, 0011. That means whenever your middle orders or the last 2 bits are 00, all those bits are getting blocks are getting mapped to your same cache line. What is the difference? Difference is that, let's see, you are consider your practical example of instruction memory. You have written some program and that has been written in your main memory in some 00s, all 0, all 0, 0001, 0010, 0011 in this way. Gradually, it has increased this, changed this bit, like a counter, and there you have written your instructions. Now, if you are following high order bit indexing, what will happen? All 0 bits, that means all 0, 0001, 0010, 0011, all these locations are getting mapped to one single 4-bit 4-line cache. Okay. You can see this. You can see all this. All these 4 locations are basically getting mapped to this single cache line. Now there is a high chance that whenever you are actually writing that your instructions, your instructions are getting mapped, like the related addressing is done in this way, that your instruction 1 is here, 2 is here, 3 is here, 4 is here, this way. That means whenever you have done with instruction 1 and then you are going to instruction 2, your block from that cache is getting replaced with instruction 2, the related memory entries, then with 3 and then with 4 and so on, right? So there is repeated replacement from your cache. Now you think in this way, if this is not a general sequential execution of instructions, this is a loop. That means what will happen? You will execute one replacement is taken. That means whatever entry was there for your this block 1 or instruction 1, that has been removed from your cache. Again 2 to 3 you are going, again removed from your cache, 3 to 4 and in this way. So whenever you are repeatedly coming back to 1 or repeatedly executing this loop 1, 2, 3, 4, 1, 2, 3, 4 and so on, there will be huge number of cache replacements, and that way each time whenever you are actually encountering your this location instruction 2 related instructions or data fetch, every time you have to face some cache miss, and again you have to go back to the main memory, again you have to load that data to your cache, and then you have to fetch them. So chance of increasing your chance of facing your cache miss or number of cache misses will be high. In that way, your overall performance, in spite of the fact you are using the cache, your overall performance due to this the repeated encounter of this cache miss will get degraded. Okay, so this type of concept which is called spatial locality. Okay, so in spite on the other hand, if you do your if you do the indexing in this way, see here all 0 0 1, you are doing the indexing with 0 0 0 1 1 0 1 1, all within different, you are mapping to all different cache blocks. In that way, what will happen? These all 0 will get sorry. Here, this is the this pink, then the next pink. Those are widely separated. Now, if you are actually executing your loop, what will happen? Your location, your instruction 1 is present in all 0, maybe. Instruction 2 in again 0 0 0 1, instruction 3 in 0 0 1 0 and 0 0 1 1. But they are all mapped to some different cache blocks. That means cache lines or cache blocks. That means whenever you are actually executing 1 and then after that you are coming to 2, there is no requirement that you have to replace the entries related to block 1 or instruction 1. That means the whole loop you are executing, you are just fetching your data from the cache. There is a high chance that every time you are getting cache hits, and that way for that particular loop execution, your performance is getting improved. So this is the way how, this is the important concept, that effect, that how you are indexing your main memory blocks and how you are mapping that to your cache, that has a very important effect on your overall performance. Okay, is it clear? Any question? Everything is clear?
No, ma'am.
Hmm? It's not clear, right? Which part? You tell me, I will repeat that part.
Clear, ma'am. Clear, ma'am.
Clear, okay. So this is the concept of cache. So what we have discussed so far, that there are two things. Both are, whenever we are talking about memory, everything is related to some amount of mapping. Okay. Whether you are mapping your virtual address to your main memory, okay, that means you have some backing store where we have stored some instruction or data, and due course of your CPU execution, instruction execution, you are fetching them that memory related information, and that you have to bring to your main memory, to your actual physical memory, and then your CPU can execute. This is one concept. And next concept we were discussing, when, okay, in your main memory you have divided different blocks, that is fine, but you want some faster execution. Then in intermediate, you are using some concept of intermediate buffer, intermediate faster some storage unit. That may be costly. That's why the technology behind the cache development is costly. That's why we cannot actually support this faster memory for our main memory. But what we want to do, that is we want to reduce the number of search. We have maybe huge number of rows in our main memory. If you keep some track of our recent executions and we keep the mapping to some intermediate buffer, that we expect that improve our overall execution performance. Execution time. Of course, there is a chance, we have discussed in both the cases, we have seen there is a chance of hit and chance of miss. If we are using intermediate buffers, concepts are both the same, that wherever you are using some buffer, intermediate buffer, at that time there is a chance of hit and chance of miss. So whenever we are actually doing some analysis in terms of our execution, in terms of software development, timing analysis, we have to consider those possibility of miss also, and then we have to compute the access time, total access time. Okay, so these are few types of cache. Okay, where again we see that we are adding some hierarchy. So these are we have already talked about this L1 cache. Okay, you can see D cache and I cache. Maybe you can think in this way. Whenever you are writing something in the processor, first closely coupled memory storage unit, that is your register. From there, the register is getting coupled with this cache, and this cache is maybe data cache and instruction cache separate. In some parts, there is maybe some overlap. Based on your architecture, you are keeping them separate or you are keeping them together. And then there is something that is called L2 cache. Okay. From that L2 cache, we are going to the main memory, and then this is the disk or something that is our secondary storage, we can think. So this is our primary storage, primary memory, secondary storage. This is the L2 cache. This is smaller. We are dividing this L2 cache again in data and instruction part, and that is our cache. So we can see that this way our performance is improving. If we have just followed the idea of just accessing this memory and from memory to disk that way, that is not good, or that is not suitable for our performance improvement. So the more we are using, coming to the cache side, also better than that is register. So those type of executions require lesser performance. Those are lesser performance costly. So this way you can see the arrow is showing this side is larger, slower and cheaper, and this part is costlier, faster and also smaller. That's why there's a chance of miss that we have to, in spite of the fact we are expecting some gain, but also there is a chance of this effective misses we have to handle properly. Okay. So this there are some other concepts of software caches. So like file system, web browser caches, those are software caches we consider. So those are typical simple storage unit, but since we use them as buffer, so we sometimes term them as software caches. Now we will take one example. Okay, so maybe that example, the same thing, maybe we are talking about the loop handling. See, you all are software designers. So whenever there is this type of example, this is a simple code or summing up some array values. Okay, you can see this is a sum array. It is based on row major idea. So you are actually considering this this array A with m row and columns, and you have started your execution for I is equal to 0, I less than m, I plus plus, and this is you are traversing over the columns, and you are doing the sum plus is equal to a I j. Okay, that, and then you are returning this. The same problem, the same sum computation, someone is doing with this way. Okay, first you are considering this, you are traversing your row over n, and then you are traversing this row over M. Whereas for this M cross N matrix, you have traversed your first row over M and your first row, second for over N. Okay. So first row, then column, then second column, then row. In both the cases, your answer will be right. Correct? Yes or no? The answers will be right because every time you are actually adding this, gradually you are adding these Aij values. But where is the difference? Both are correct software designs. I mean, whenever you will handle these loops without any knowledge of behind architecture or this cache or whatever going on in your backend memory, both execution will be correct, but it will differ in terms of performance. The reason is maybe whether you are using the C or any other language or any other platform or processor, based on that, this performance will heavily differ. The reason is the way, see, every time you are fetching this value Aij. That means somehow this value was in your main memory or your backend memory you have stored initially. From backend memory, since this process is in execution through swapping technique, remember whatever we have discussed. Through swapping technique, you brought those parts to your main memory, right? From main memory, that means you can go back to this. If your data was here in disk, with the swapping technique that we discussed initially, you brought the data to main memory. From main memory, again, you have to fetch this data to your cache, okay? And then you will do this execution. Now the question is, whenever we are storing this matrix, these 2D matrices, different platforms, different processes, and different this type of C, Fortran, those languages, their compilers, they handle or they store whenever they are storing in the backend, they store these arrays in different ways. So in one case, we can see in a case of C, it stores the matrix in this form. Matrices in this form. This row major order, 0, 1, 2, 3, and so on. In this case, in case of Fortran and all, they store in column major manner. That means whenever you are writing your code in your row major manner or in column major manner, what performance you will get, that will entirely dependent, that is entirely dependent on which platform or which background you are actually using. So if you are actually using something like this, where column major storage has been used for your for your 2D matrices, 2D array elements, at that time, if you have written, now if you think there you have written some row major related code, okay, so that time whenever you will be fetching your rows, there is a possibility that your chance of cache miss will be high. Or on the other way, we can see whenever you are actually accessing your next element, if it is supporting your code is actually getting support with your backend hardware, of course you can understand that when there is lesser chance of your cache miss, your performance will get improved. So that way, whatever you are writing, it may be the fact that both are correct, but one implementation, one coding is going with the knowledge of your backend hardware, of your backend memory or backend whatever, maybe some pipeline strategies, hazard concepts. If you are known to those things, in which platform you are using, of course, in pipelining case also we have seen, you can arrange your instructions in that way that you can fill some no operation with some later, future instructions, so that you can actually avoid some delay, and it can make your execution, it can improve your performance, it can reduce your required timing. Same thing here. If you also have the backend knowledge of your this cache, or how your data, whenever you are taking an input, how that is getting stored backend in your memory, then those access times, your memory access time, maybe it is from the cache, maybe it is from your main memory, that may directly affect your actual execution time. So that's why we have discussed so many things about this memory and these pipelining strategies, because they have direct effect on your on your cache, direct effect on your analysis. Because if you cannot do that performance analysis, you will not know in your embedded scenario, you will never know that whether this implementation is worthy or not. If you do this loop, there are thousands of loops in your execution, these types of loops maybe, and when it is required to have some row measure execution, maybe that could have saved some amount of time. You have done some column measure execution, and in those cases, maybe your requirement of each per block, or you can say this is one block, per block of such loop execution is high, that will in turn affect your total performance, and that for that you may miss your real time deadline requirement. That may increase whatever, that may badly impact on your overall timing requirement, and that may affect in such a way that you may miss your deadline. If that is the case, there is no point in case of your embedded design, that this part is very critical, because in that case, whatever you have developed, that is of no use if that is not satisfying your embedded real-time requirement. So for this reason, these type of knowledge, backend knowledge, for a good embedded software designer, these type of backend knowledge, how they're affecting your performance, that is very important. Okay. So this is about a few words about cache and main memory. Next, we can see some terms again, that one is you can see that when we are actually considering our CPS cyber physical system components. So there we see there are different requirements of adding peripherals to our system. So this is not only for data memory, not only for instruction memory, we should also think that how we are handling our peripherals, right? So for that, let's say what we know, that we have to give instruction to some of our peripheral or some IO unit. So far whatever discussed in from the concept of our instruction set architecture, that remember, we will define some opcode, we will write some opcode, and when that opcode, we will search in our instruction decode stage, we will search what that opcode means, and according to that, we will give the instruction. Or we will fetch some data from the memory and we will pass that to our peripheral. That is the step we have learned so far. But when we know that our peripheral is just some IO device, maybe that external device just needs some input, and every time either it will read some input or it will write some input in some particular location. So for that, there is no need to define another extra opcode that will again go for the whole stages of instruction fetch, instruction decode, then execute, then fetch from the memory fetch, and all the whole steps. And that also after searching the whole instruction memory. Rather than that, we can just go straightforward with some memory map strategy where we can associate some few specific memory locations where we will put that data for that external device. So as and when required, that external device can take that data from there, or that external device also can put to that particular location some values that our CPU during due course of execution that can use. So for this, because when these type of what to say, this type of communication with these external devices or peripherals, you can see peripheral bus, or with them, when this communication is very frequent. So if we try to go through the whole conventional step of those 5 cycles and then coming to the doing the same execution, then that may take a lot of time and that may reduce our overall performance. To avoid that, we are actually using this memory mapping technique where we have kept memory map these external devices, or in some cases memory map some registers or some peripherals. Through that memory map concept, we will actually do this communication. Okay. So this way, this is all about what we have in the backend, what we have in the cache, how that is communicating with our main memory, what is the concept of virtual memory, etc. But in general, why we prefer software actually? We prefer software because it gives some amount of abstraction. Maybe we do not know so much thing about the backend. Some knowledge will be of course helpful for the better execution time, improvement of our software. But without that also, whenever we are writing some code, we are executing some code, these are the five parts of memory that is we are actually thinking or we are actually considering. What are they? Whenever you actually next day we will take one example, whatever we are writing, and we will see basically we are considering some initialized data, some initialized data, and some stack, program stack. Why they are used? They're used for to store some local variables. You are defining some functions, function return pointers. So for those, these stacks are getting used. And some heap, that is for some dynamic memory allocation. Okay. So this heap can be, that is not very static, that may be growing. So we have some typical functions, calog, malloc, some typical functions to allocate some dynamic memory, and that memory will help me in my instruction execution. Otherwise, I will write some functions. I will just write the variables. My operating system will take care of storing those variables, and for that it will use some stack. Also, some one function I have to jump from one function to another function. For that, some function return pointers, whatever it may be. So all these things will be stored in the stack, and for dynamic memory allocation, I will use some heap that will be that I can control how much memory I will require, and that I can control dynamically. And that way, this is, as a software engineer, that is the view, that is the application memory view only, that that is known to me. Or basically we work as a software designer, we work only in these parts. In the back end, everything is taken care by the operating system and later on in the hardware part. Okay. So this is a view of the application memory, basically in which part a software engineer deals with. So this is a few words about the memory or memory organizations and how they affect in your software design. So now tell me, what are the questions? Okay, buffer and cache. Okay, see. cache is a buffer is used for storage. Why I have used that time the buffer and cache interchangeably? There are few differences. But cache is an intermediate memory that is acting as a buffer. Buffer means that is intermediately storing some information that may be replaced somewhere. Whenever you will actually bring some new block to the cache, old blocks will be replaced. Okay, so that's why it is just I have that's why I have used those terms interchangeably. That is acting like a buffer of intermediate storage, just to improve the performance, just to decrease the fetch time of any instruction or data from the memory, from the main memory. Actually, that is the concept. Okay.
Hello, ma'am.
Yes.
Ma'am, please give the example of this. I am unable to get this difference.
Which one?
Cache and buffer.
Cache and buffer. Cache and buffer, those terms I have just used interchangeably. Why? Because cache means what? Just think about a cache. Cache means it's a smaller memory, right? It's a smaller memory means you have number of rows, whatever you have in your memory, in your cache, that is very less. That's why you need some amount of intermediate replacements. Like whenever your one cache line is full and you have to store another new block from your main memory that is getting mapped to the same cache line, you will replace that the older data and you will fill your cache line with the new block of from your main memory. Correct?
Yes, ma'am.
So buffer means what? Buffer is an intermediate storage. So that's why I have used this term interchangeability, that at that time this cache is holding that data and acting as an intermediate storage, and that is something like buffer. Okay.
Yes, ma'am. Yes.
What else? Tell me. Otherwise, I have a question. Okay, maybe who will answer? Let's see. Someone random. Whose name is first here? I can see. Maybe that's one. Vinay, you are here? Vipul is there, right? Last name is Vipul. Vipul?
Yes, ma'am. I'm here.
Okay. Okay. Can you tell me that you have one specification? Okay. This is your, general Viva question, I'm telling you. Then you have to, you are an embedded software designer, then step by step what you will do. Whatever we have discussed, based on that, can you tell me that what you will do? Starting from your specification. You have got one specification, then next.
So my first step would be to understand what product I have to design. So the software for what I have to product for design. For that, I need to know what are the requirements that I need to provide.
Okay, you have your requirements then.
Such as the deliverables. After that, I need to know on what specifications will the system work, the processor memory, the processing speed, stuff like that.
How will you know that beforehand? Okay, you tell me, then I will come to it. Okay.
Okay, there are the two scenarios. There are two scenarios. One of the scenario would be considering designing the processor itself. In that case,
no, I am not asking designing the processor. I am talking about you are designing one embedded software. You have some options of your processor. Then how will you choose?
Okay, so how will I choose? Based on the customer requirements, we would know. So, for example, if we are designing an IoT application, what could happen is we would be provided with some sort of a sampling rate that the sensor provides. So, based on that, we need to choose the CPU that will be required.
Okay, before that is coming in the design phase. Whatever you are telling. Right. But before that, what we have discussed. What is the first thing you will do? First is the modeling part, right?
All right. Yeah. I was going to come at after that modeling part. I mean the FSM
Okay.
part, right?
Okay. Okay. Tell me. Okay. Design part you tell. Then someone else will tell. I
Okay.
will come.
After that, what I would consider would be is the modeling part where I would design the finite state model of the running software.
Okay. Finite
Uh,
state model. Okay. FSM.
yeah.
So, okay. Then,
I mean, and from there I could design the UML part. I might be losing the order here a bit. I'm sorry for
yes,
that.
that part you should be cleared. Okay. Okay. Someone
Yeah,
else
yeah.
maybe. Okay. Maybe we boost that.
Can I try?
Okay. Who else next? Vinay is there. Next name. I can see whatever there in the. Then Vinay is there. Can you Vinay tell
Yeah.
something? Yeah. Vinay, you have some specification. Then
Ma'am,
what
first,
will you do?
after, I mean, we got, ma'am, can you tell that? I mean, I have some issue with network here.
Okay. What I am asking that you got your specification. Okay. Then after that you have to do
Yeah,
design one embedded
okay.
software. What will you do next? What will be your step?
First is to identify the requirements. We model it. Initially, we will model the system using
Okay, how will
FSM
you
or
model? How will you how will you model? You have to choose some modeling technique, right? What basis will you choose?
Yeah.
You have to check.
Depending on the statements available, I mean, there should be a problem statement.
Of course, problem statement
Whatever
is
is
there. That's
available,
what
the
I'm telling you.
specifications
Have
of the
your
problem.
specification, some specification. Now you have to model it. Now you have to choose your
Yeah.
first thing is that two things are crucial,
Yeah.
right? You have to first choose your modeling technique and then you have to choose your
Yeah.
which platform you will work on. That will come later in the design phase. But in your modeling technique, how will you choose that?
The depending on the constraints, I mean, whether it is real time or those kind of considerations.
Okay, so what will be the different? If it is real time, then what will be your modeling strategy? And if it is not, then what will be your real time? What will be your modeling strategy? I mean, what will you choose? First tell me.
For real time, like there will be time bound conditions, like there should be very strict specifications regarding the times, etc.
Okay. So, yes, that is the requirement
So
of
for
real-time
the
system.
other,
You are correct. Then I'm asking when you will be choosing some modeling strategy, how will you decide that which one I will choose? Okay, maybe next one, someone. What is the name? Vaibhav. Vaibhav is there? Okay, Vinay. No problem. Vaibhav? Vaibhav is not there, it seems. Okay, Gautam? He went to sleep, maybe. He's online but went to sleep. Gautam? Yes. Gautam, can you tell? Yes. Can you hear me? Hello? Yes, there is some problem. Hello?
Hello. Hello.
Hello, yes, tell me. So, what are the different modeling techniques you know? And how will you choose? You have some specification.
Starting with it depends upon continuous continuous inputs are outputs. We will go continuous input and also discrete you go for state machine on states for machine go. Hello. Hello.
Oh, okay. And if you are doing some
Hello.
project, yes, your voice is breaking actually. Hello?
Hello.
Yes.
I'm having.
Okay. I'm asking if you see that your specification includes the strong what to say, data modification kind of thing, data filtering or something like that. So do you think in that case also you will choose this FSM or extended FSM or something like that?
In the data, we go for data flow model, no ma'am. Then there are streams of
Data flow.
input data. We have to filter them out.
Yes. So that is the case. That that is I want to tell that whenever you have some specification, it is not that always you are jumping to that set chart or set flow, those things. It is based on your domain of your specification. Maybe you can choose your modeling technique. Okay, so there, if there are some huge concurrency or those type of requirements, so that time you can also choose the SpecFinet kind of thing. Okay, so these are the different modeling techniques, and there are many more. You can choose the modeling. So that way you have done with your modeling, and you are getting clear with your modeling technique. Sorry, you are getting clearer with your given specification. Okay.
Sure.
Okay. Next, who else? Sukhvinder?
Yes, ma'am.
So after that, what will you do?
After getting the
You have done your modeling. You have got your specification. You done your modeling based on the given scenario. You have chosen your modeling technique strategy, and you have done that. Then after that, what will you do?
And then I'll choose the components then according to my specifications, which I'll use. Like I have made a model of that. Now I want to implement it in a physical way. So I'll need some specified component. So according to my modeling, according to my model and my specifications, I'll assemble I will assemble different parts. Like I'll go for the you can say I can't I'll not use for the sake of memory. Like if I require only 10 MB RAM, I can't just go and pick a hard disk for 1 GB or something like that.
So so first thing is that for that, do you have the open option? Is it that are you planning to make a custom processor, or are you building on some existing processors? Maybe some general purpose, or maybe some some microcontroller you are choosing. So your decision will be based on that, because in spite of the fact you need a smaller memory, it is not that, in your custom-made design, of course, you can choose in that way. That is the difference between your custom processor and if you general purpose. But based on,
yeah, but even if I'm using a specified I take a system like Arduino system. In that system also, I'll be using some specified registers which I'll be which are required.
You will be using, but you cannot choose your platform that way, because those are restricted, right? Okay.
Yeah.
Then after that, what you will do?
Ma'am, I'll implement the the model in the physical form using the parts I have. Like you said, restrictions will be there, but
how it okay, what are the feature things you will take care of whenever you are choosing or you are writing your program?
Ma'am, it should be the first thing, it should be stable, ma'am, and more efficient. It should work efficiently.
How will you know efficiently? Efficient means what?
Ma'am, so before
maybe next figure. Yeah.
Ma'am, before choosing the processor, do we not need to simulate it first, so that we can actually check that how expensive would our code would be? Even after modeling, we won't be able to tell easily how expensive our code is, so we would probably have to simulate it. And
so whenever you do simulation, Have you used any simulation? Environment.
Yes, ma'am. I've used Gazebo, ROS-based simulation environment,
Okay,
and
that means whenever you are doing any simulation, that time also in the simulation environment, we also consider some type of future processors, right?
uh,
When we do hardware simulation also in FPGA,
yes, ma'am.
there are different. Yeah, I understand whatever you're telling. It is called the behavioral simulation. Okay, behavioral simulation means we are checking whether our functionality is correct or not,
Yes,
right?
ma'am. Yes, ma'am.
Yes, I got it. And in simulation, actually, we will do that in the lab. You will see that after behavioral simulation, we do in FPGA kind of thing. I'm telling you that we do pre-route, post-route, those simulations. Those means that time we are just not simulation means not only that we are considering only the behavioral or functional parts. Okay, it is sometimes we are considering that whatever future platform we are going to use, processor we are going, maybe some Vertex platform or whatever we are going to use, and we are checking based on their constraint whether my blocks will be is it okay to get mapped to them or not.
Ma'am,
That means
as in that
yeah,
that processor can that platform can
or
handle
not
my.
exactly hold my design or not, or that processor has the register capability or that memory capability, RAM capability, everything is there or not. And also that finally we check the routing requirement. If with the whole routing also, after the whole routing, we are actually getting satisfied with our real-time requirement or not. That means our real-time, whatever requirement, timing requirement is there, that part is whenever the routing within the intermediate blocks, after that everything, whether it is got satisfied or not. So those parts also we can do in the simulation environment. Simulation environment not only means that we are just checking the behavioral parts or the components.
Yes, ma'am.
Okay,
And
so that is called pre-route or post-route components.
then, ma'am, after the simulation, then we'll like you had told before today that we are accessing it using row first or column first. So that would depend on how my platform is actually implemented. So those optimizations will take place later when I've chosen my platform. Like, is
Yes.
that right, ma'am?
So yeah, that is a thing that we will consider now, whatever platform we are choosing and what is the effect on that in our design. Okay. So this is one thing. So next, Siddharth.
Hello.
Yes. Siddharth, can you tell that whenever you are doing some timing analysis of your software, that means you are checking, okay, I can be using this or language constructs I can write. So what are the factors you will consider?
Now, firstly, the variables we are using in the main modeling system and the main program, and after variables, what are the space requirement in the hardware we are using, and what hardware speed we are getting from the basically when we are using a clock
Yes,
source.
Richard. Space requirements, you are telling what is the memory requirement, right?
Yes, ma'am. Yes, ma'am.
Yes, okay. Then what you are telling, what is the hardware? Pardon, what is the term you have used?
Ma'am, basically, on which speed the basically hardware running when
Hardware running means I'm not getting.
basically the hardware mainly using a clock for this
You are telling machine
all
cycle
process.
or clock cycle. Okay.
Yes, ma'am. Yes,
Okay.
ma'am. So,
Okay.
so when we are fetching the data, or basically, or basically using any data, what can I say?
So
Mainly just
what are the features? I mean, in the backend, or one is that okay, machine cycle or the clock cycle you are telling. Okay. And what are other features that can affect your program? What do you think? That we have already discussed, right?
yes, ma'am.
What do we have discussed last day? What are the features?
Basically, how we just
Whatever we discussed last day, the pipelining part, right?
yes, ma'am. Yes.
There we have seen that the most important thing we have seen that our instructions, how they are oriented, what are their dependencies, because pipelining support your hardware can give, but it is based on your dependency on your of your respective instructions, that whether you can take the full or some part of the partial advantage of that pipelining or not. Because you think if your instructions are too dependent, and in every case you have to add additional additional no operations, or adding additional delay operations to handle your hazards, then there is no point using the pipeline processors, right? In those cases, the simple straightforward processors are better, isn't it?
Yeah, we can use timers for basically for delay purpose, and we can use interrupts for so that we not require basically no operation function.
No, that time you will use the interrupts for no operations. How can you use that? Can you tell me?
No, actually, when we basically doing all process, basically when we needed two processes mainly at the same time, like delaying and mainly at the same time, we require motor control. So, for getting basically shifting for the new register, we giving the timer to get delayed, and in between we can control the motor also by basically mainly interrupting function.
Okay, that time you are adding one delay in that hardware, because but here we are talking about the hardware within your processor platform. Okay, in that processor, if you want to delay something, you have to skip few that your pipeline hardware, they are asking for some inputs. Okay, you have to give some inputs to them, but here you are adding some delay. Means what? You are giving some inputs so that there will be no effective output. That is called the no operation.
Okay.
Okay, the way you are providing the inputs to your ALU at the back end, basically they are not actually giving you any operation. That in turn is giving you some delay.
Okay.
Clear? That is a concept of no operation.
Yes,
that is, you are delay means here in the hardware you are adding some no operation instruction. You have done your microcontroller programming or something like that. There you have used some no operation execution, right?
Yes, ma'am.
I think you have done it in your lab also. You have done it. We frequently use it.
Yes, ma'am.
So I'm asking, what are the different features that will affect your performance or software performance? That is, you are adding delay. Okay, go through it. Whatever we have discussed, like
Yes.
right, pipeline, whatever. So these are very simple Viva questions I will be asking, nothing else. That what you will do, what will be your decision making strategies in different cases. Next, Pratiksha.
Yes, ma'am.
So can you tell what are the different features that will affect your design or you will take care of?
Yes, ma'am. Mostly, like we will be looking at pipelining things. So our whichever, like whatever we do, hardware and software should be compatible to the overall structure. Otherwise, like we'll have to take care of, if we are programming it, then we have to make sure that our hardware also supports it. And if we are using the hardware parallel hardware, then we have to make sure that we have software also, like we have the proper codes which we have used to like make it sure to get
No,
the
of course.
thing
So
which we
whatever you will write, that you will write the software. Of course, you will write in a supportive, languages, and you will use those instructions. I mean, in the language of those instructions. Like in your C, let's say you have if A greater than B, then do this, then do that, or your that way add, subtract. These operators you will be using. So that is okay. So how you will
Yes.
manipulate those to map with your backend architecture? That is the question. To get the best performance, that is the question. What will you do with your code?
Means, ma'am,
Because
like
you are the
like
software developer. You have only the software part in your hand.
yes, ma'am. Ma'am, then we could actually make it sure with the help of memory organization.
Memory,
So
okay.
by
What will you
yeah,
do in a
my-
memory organization part?
yeah. No, ma'am. Like we could program it such that like the time sensitive things like the which are very much dependent on time, we could actually program it in a way that we use most of the cache memory to execute such a time sensitive, and we could actually get the time of execution and all through the memory understanding of the total memory architecture or the organization.
Okay. Actually, not always. It is for a software developer. It is not always possible to know. Okay, you can have a overall view of your memory organization. Okay, what else?
Ma'am, then there are lots of like the other day we have seen lots of methods of parallelism like to be achieved through various process like superscalar or VLIW or instruction sets, various instruction sets.
Okay, good. Yes, it goes. Okay. Okay, then Nilesh?
Yes, ma'am.
Yeah. Can you tell what other features you will take care of?
Ma'am, first of all, I will take care of the power consumptions by reducing the number of transitions. Ma'am, as a software developer, what will I do that, ma'am, there are, I have studied in architectural design class that if if we are using a tree logic, sir, ma'am, there are two logics. One is simply that if we have to produce uh, uh, we have taken two AB inputs and two CD inputs, providing to the two AND gates and connecting both the outputs of the two AND gates to the third AND gate. This will take more power, because as the transitions are more, because if we will when we will draw the truth table of first this type,
So can
it
you
will
tell me why do you think these transitions are more?
uh, ma'am, it will ma'am,
I
because
mean, why the power consumptions are more?
yes, ma'am,
Okay,
yes,
transitions are more, fine. Then why do you think the power consumptions
ma'am,
power consumptions are more?
consumption is more because if we add a capacitive load to the output of these gates or logics, then
No,
it,
you are a software designer, Nilesh. You do not have that capacitor or those things in hand. You are
ma'am, like, but
designing on embedded
ma'am,
software.
yes, ma'am, but
So
I can simulate it in the software too.
whatever you
For test
simulate, you
for test
have some language in hand, you are writing some instructions, and you are making your,
No,
execution,
ma'am, no, ma'am. Ma'am, you asked that how this transition is going to consume power. That
yes, I got it. I'm asking if you are thinking about in terms of embedded software writing.
yes, ma'am.
There also similar logics are applicable. So, in which way you think that that will directly affect your power consumption or those things? The way you are writing or the way you are designing, in which
Yes.
part it will affect? Whatever
Uh,
you are thinking in terms of your hardware design point of view, right?
yes, ma'am.
Yes, I'm asking you as an embedded software designer.
Then, ma'am, for less transition, I have to optimize my code. Means I don't have to, for example, if I am swapping two numbers, I don't have to use a third register because it will take one more transition. So I have to only use two registers. This
Okay.
from this type, I will reduce my power
Okay, one
consumption.
is transition reduction. Okay,
Yes,
that you can do in your modeling technique also. The data
yes,
flow.
ma'am.
Whenever you are doing this modeling, no need to go
Yes.
that for the to the up to the till the implementation part. So what else?
Now, ma'am, we can also mm, reduce the delays
Reduce the
because
delays.
yes, ma'am. Because there are what is happening that if we are
How
let
will
us
you
say
reduce the delays?
yes ma'am, I am telling ma'am, can I take an example for explanation?
Yes.
Ma'am, if we are using let us we have to sum 1 to n numbers. If we are using n number of adders or not in hardware, ma'am, in software, let us assume that we are taking a for loop and implementing the soft codes from 1 to n and running a loop of I plus plus.
Yes.
Then it will take more time, and while calculate if we calculate this by the same formula n plus 1 by 2, then it will not take very much time. So I am saying that we have to calculate these things by our own and
Okay, but
optimize.
for n plus 1 by 2 calculation, that means you are, you are just splitting the array or you are doing something,
Yes,
similar type of things, right?
yes,
So
yes.
for that, what extra support you need? Can you do that always?
No, ma'am, I am only taking only in this case I can do.
No, you
For
can do you cannot do first of all in whichever cases you want to do.
yes, ma'am.
What are the dependencies you have to check? Just study the processor dependencies we have discussed.
Yes, ma'am.
Okay, whatever you are telling, to take that decision, you have to also check your processor dependencies, whatever your backend hardware or your ALU is supporting,
Yes, ma'am.
right?
Ma'am, can
Or whatever scope of parallelization is there, then only you can do that,
yes, ma'am. I got it. So yes, ma'am.
right? So just go through those parts, whatever I have discussed, we have discussed. So, and these are the few questions. Whenever you are studying, study this way, that whenever you are, these two things are very important. Basically, whatever we are discussing in this course, two things are very important. When you are in the modeling part, how you are doing the modeling, what are the things in your specification that are actually deciding which type of modeling technique you will choose, and based on that, what are the different modeling choices you have and how you are doing modeling with that. This is one thing in the modeling part. And the second thing, when you are mapping your modeling to your design, what are the your main thing of your design is your performance, and sometimes of course space, power requirement, whatever you have told, all these things. So far, we have mostly discussed about the performance issues and what are the typical scenarios or typical effects will come from your processor or your platform that will affect your performance, and how are they affecting, and which way you can improve them. Basically, these throughout this course, we have just discussed these two things. Today, we have taken that same thing in the memory point of view. The same thing we have taken the last few weeks, the pipeline point of view. So, and then we have improved those things, your specifications in data models, or you have clear or made our understanding clear in your FSM techniques, those things. Okay, these things we have mostly discussed. Ultimately, in your embedded design, our objective is to meet our real-time requirement. That's all. For that, we are thinking so many different ways. Okay. Yes, Nilesh, you wanted to tell something?
No, ma'am. I want to ask, ma'am, if you are we are saying that its performance is good. So, ma'am, what are the conditions? Because I only know speed and power consumptions and these two.
Performance is, actually, we are telling, actually, this answer will get at the end when we will do different types of validations. Okay.
Okay.
One, your embedded software is proper means you have to do different type of validations. One is your functional validation, that it is functionally correct. Second is your performance validation. Performance means your that whatever timing requirement, real-time timing requirement you have, delay requirement you have, your software is is as per with that. It is matching with that requirement. And the third one is, we will next discuss about communication, embedded communication. That one part is left. So that part and some effect of interrupt also. Next day, how they can actually affect your performance. So this part. So that the third part is your communication validation. Communication means maybe component first you have developed everything properly. Everything is working fine and everything is as per your timing requirement. But when they are actually communicating with each other, whether that is proper or not. So these type of your embedded system is validated and it is proper means you have to check, you have to analyze your design in these three parts. Yeah.
Yes, ma'am.
So this is the thing. I think. Any more questions? Otherwise.
Ma'am, can I tell something?
Yes. Tell me.
Ma'am, we can reduce the usage of recursive functions because the embedded systems that we are using, they are having memory constraints. So the more we are going to use the recursive functions, system
Next day,
stacks.
I will come to a bit about this recursive part. I will touch this and I will touch about the stack also. That I have not done this today.
Okay.
Okay, you have seen that the stack concept will be, it is required when you are talking about recursion, right? Maybe you know that you are from.
Yes.
So I will talk about the stack a bit and then I will come to that. Recursion. Without that, recursion, how it is actually affecting it is not very straightforward to understand, right?
Yes.
I will come to that. Okay, but you are right. That part also, yeah, we have to check. Okay.
And we can replace them with loops.
Yes. Yeah, pardon, can you tell me? What?
I meant that instead of using the stacks, we can use loops for iterative purpose. So it will reduce the stress on the memory and that.
Yes,
system that stack.
Yes,
stacks with loops.
Yeah, handling the stacks. So when I will come to that, I will mention about the application. Next year we will take one example and we will take. Okay.
Yes.
Ma'am, one last thing about the Viva for the groups for whose Viva is on Friday. What till which part will you ask?
Thursday one group is there, right? One Thursday and one Friday, right?
One is on Friday. So will you ask this week's topics as well in the Viva?
No, not memory part. Not memory part. Because nearly one part is all still left. Okay. Only up to pipeline. Up to pipeline.
Okay, sure. Thank you so much.
Okay. Yeah. Okay. That's all from my part. Maybe we can log off today and if you have any questions, maybe we can take that next day. Okay.
Okay, ma'am.
Thank you.
Okay, ma'am.
Yeah. Okay.